Okay, go.
Can I start?
Yeah.
Okay, so let me start with the definition of quantum proof of knowledge. And I'm going to consider proof of knowledge only for NP relations. So it's an interactive protocol satisfying three properties. We have the usual completeness property. The second property is quantum proof of knowledge, which is what I'm going to talk about in a second. And the third is quantum zero knowledge. You're already familiar with completeness and quantum zero knowledge, so I'm not going to discuss that. So let me discuss what do I mean by quantum proof of knowledge. So quantum proof of knowledge says the following. Suppose, let's say there exists a malicious prover, right? So for every malicious prover, we say that there exists an extractor such that if, let's say, the prover convinces the verifier to accept with some probability, then we want this extractor to extract the witness corresponding to this instance with probability negligibly close to the acceptance probability. Okay. So more formally, we'll consider two experiments. In the first experiment, we have the prover, malicious prover, interacting with the verifier. So it gets as input the instance X and some auxiliary state. And the verifier gets as input the instance. And at the end of this protocol, the prover outputs some state, and the verifier outputs whether it accepted or rejected. Okay, so this is one experiment. In the other experiment, we have the extractor who has access to P star. It could be black box or non-black box. It doesn't matter. And then it takes as input X and the same state which P star receives in the first experiment. And then it outputs a state and W. Okay. Okay. And we want, there are two requirements associated with this definition. The first requirement is that the state output by the prover, psi out, should be close in trace distance to the state output by the extractor. Right? So in other words, the prover should not be able to distinguish whether it was talking to the verifier or the extractor. Right? I think in this is referred to as the simulatability property. And the second requirement is that the extraction probability, this is the extraction probability, the probability that the extractor outputs a valid witness to the instance should be negligibly close to the acceptance probability, the probability that the verifier accepts in the when it's talking to the malicious prover. Okay. So this definition is a special case of Unruh's quantum proof of knowledge definition. Please correct me if I'm wrong. So in Unruh's quantum proof of knowledge definition, there were no guarantees on the prover state after extraction. And moreover, the acceptance probability and the extraction probability need not be negligibly close. So in our setting, we need both these requirements. Okay. Okay, so
can I ask just one quick clarification?
Sure.
Don't you actually need, if you go back one slide, don't you actually need to consider something about like the joint distribution here? I mean, you want basically that like, you know, that the joint distribution, say, on the final state conditioned on the verifier accepting should always be the case.
Yeah, I mean, in some sense, these two requirements are just one requirement. Yeah. Yeah,
well, I'm saying that the one, you know, requiring something on the joint distribution is a little bit stronger.
Yes, and we need that requirement because we need the joint distribution requirement because if not, let's say the prover is able to convince the verifier to reject, right? And in that case, then there won't be any guarantees on the indistinguishability of the prover state and the output of the extractor. Sorry.
Right. So I guess the point is your proof will probably show the stronger property.
Yeah. Yeah.
Okay.
Okay. Um, okay, so we can generalize the definition to the bounded concurrent setting as well. So in this setting, we require completeness and quantum proof of knowledge as before. But in addition, we want the protocol to satisfy a stronger property called bounded concurrent quantum zero knowledge property. So I'm not going to discuss this in detail. This was covered in one of the earlier reading group talks. So I'm going to very roughly say what it is. So in this definition, this is a stronger definition than the standard quantum zero knowledge. So in this definition, the prover can simultaneously interact with many verifiers, let's say Q verifiers, where Q is fixed ahead of time and the protocol parameters can depend on Q. And we want the guarantee that the output distribution of all these Q verifiers in the real world should be computationally indistinguishable from the output of the simulator in the ideal world, where the simulator has access to all these Q verifiers. Okay. So what we show is the following result. We show that there exists a bounded concurrent quantum zero knowledge, quantum proof of knowledge protocol for NP, assuming QLW. QLW is just learning with errors, where we conjecture that it's also, LW is also hard against quantum polynomial time algorithms. Okay. So for most of the talk, I'm going to just focus on constructing quantum proof of knowledge in the standalone setting. And towards the end, if we have time, I'm going to show how to extend the same construction we have to the bounded concurrent setting. Yeah. Okay, so for now, let me focus on a simpler goal, which is 1-bit extraction. So the goal is to extract just 1 bit from the prover. And in order to do that, the main tool we are going to use is oblivious transfer. And for those who are not familiar with what oblivious transfer is, here is the definition. So in an oblivious transfer protocol, we have a sender and a receiver. The sender has 2 input bits, M0 and M1. I mean, you can also think of M0 and M1 as strings, but for our setting, we only consider M0 and M1 to be bits. And the receiver gets as input a choice bit. And the sender and receiver can interact with each other over many rounds. And in the end, the receiver is supposed to output MB. And in terms of security properties, we require 2 properties. The first property, which is security against sender, roughly says that the sender should not be able to distinguish whether the receiver had its choice bit to be 0 or 1. And the second property, which is security against malicious receivers, says that the receiver should only get one of the 2 input bits, either M0 or M1. Okay. So formalizing this property is a little more tricky, so I'm going to postpone formalizing this property to later. So you can also consider simulation security, which is stronger. The reason why we are not considering simulation security here is because we don't know how to use simulation security to construct bounded concurrent QZK. So for the standalone setting, you can use simulation security. Yeah. Okay. And in terms of the computational power of the adversary, we can consider the sender to be either QPT or unbounded, and even the receiver can be either QPT or unbounded. Both of them cannot be unbounded, but you can have one to be QPT and the other to be unbounded. Okay. Okay, so here is how we are going to do 1-bit extraction using OT. So suppose, let's say W1 is the first bit of the witness and the extractor wants to extract W1. So what the prover is going to do is the following. It's going to pick bits B and alpha uniformly at random. And then it's going to assign M0, M1 to be W1 alpha if B is 0. In other words, it puts W1 in the first position if B is 0. If B is 1, it puts W1 in the second position and alpha in the first position. Okay, and then the prover and the verifier interact with each other using an oblivious transfer protocol, where the where the prover plays the role of the sender, OT sender, and the input to the OT sender is going to be M0, M1. And the verifier is going to play the role of the receiver, and it's just going to set the receiver's choice bit to be 0. Okay. And after the OT protocol completes its execution, at the end, the prover is going to send the bit B to the verifier. Okay. Okay. So if the protocol is clear, let's try to see what happens in the case when the verifier is malicious, and if the prover is malicious, how can we extract this 1 bit? So if the verifier is malicious, then you can argue that the success probability is negligibly close to half.
Sorry, just to clarify, we don't care about any zero knowledge kind of property at the moment, right?
At the moment, yeah,
because we leak one of the bits with probability 1/2, if I understand right.
Yeah.
Okay.
So later on, I will talk about how to make sure that this bit is only leaked with negligible probability. Yeah. Well, not this bit. When we consider the whole witness, it's only leaked with negligible probability. Yeah. Okay. So in this case, the malicious verifier can successfully recover W1 with probability negatively close to half. And to argue this, I'm using the fact that the security of OT holds against malicious receivers. Yeah. I'm going to make some of these things more precise later on, but intuitively, from the sender privacy property, it follows that malicious verifier can recover only with probability close to half. Okay. Okay. So what about in the case when the prover is malicious? So in this case, we are going to come up with an extractor that can extract W1 with probability negligibly close to 1. And we are going to use Waterous rewinding to do this. Okay. So what the extractor is going to do is, instead of setting the receiver's bit to be 0, it's going to set the receiver's bit to be B prime, where B prime is sampled uniformly at random. Okay. Okay.
Sorry, can I just maybe ask a clarification? Well, what's forcing the prover to use W1 at all? I mean, why can't it just set both of the bits to random? I mean, and there's no check here.
Yeah, so for now, assume that the prover is being honest. We're going to handle malicious provers by adding a zero knowledge protocol in the end. We're going to make the prover.
Okay, that's fine. So it's like extraction from an honest prover.
Yeah, for now it's just from an honest prover. Yeah, exactly.
Right. So actually, Prabhanjan, I had sort of maybe a related question of like how, like I think I lost the forest for the trees here. So the overall protocol is going to be something like, engage in this witness transfer that you're describing now with each bit of the witness separately, or maybe some encoding of the witness.
Yeah, good.
And then actually run the zero knowledge proof, the sort of the proof of the actual statement that you're trying to prove somewhere. Is that?
Yeah. So maybe let me give the high level picture first, and then I'll come back to this. Okay. So just to answer Adam's question, so let me give the high level picture. So the way the protocol will be designed is as follows. So you will have many sub protocols, where in each sub protocol, the prover, let's say it gets as input X and W, it inputs the first bit of witness here, and then the last bit of witness, last bit of W, and finally we'll have a zero knowledge protocol, QZK protocol here, where he sort of proves that he has behaved honestly. And we're going to use the extractor to extract each bit of the witness separately, right? Yeah, W1 to WL, let's say. Yeah, Adam, does that answer your question?
Yeah. There's some original relation that the prover is trying to prove. Does that also enter into the final?
Yeah, so when he say he has behaved honestly, he will be proving that he actually put the witness in these protocols.
And
right?
The witness satisfies the relation.
Yeah, witness, that's how he'll prove that it's actually a witness, right? Like he'll say that whatever values I put there, this goes back to John's question where he asked, what if you put both random values, right? But here is going to prove that, there exists a bit in each of these executions, such that if you look at concatenation of all these bits, then this is going to be a witness for the.
Got it.
Yeah.
And I guess you're going to work with some encoding of the witness so that even if you learn half the bits of it, you get no information on the original.
Yeah, exactly. I'm going to just secret share every
Yeah.
bit.
Okay. Thanks.
Yeah. Okay, so the extractor proceeds by just putting B prime in, as the receiver's bit. Okay. So the probability that the extractor is going to be able to extract the witness is going to be roughly close to half, right? This just follows from the receiver privacy property. And note that the prover should not be able to know whether the receiver used 0 or it used 1, right? Otherwise, it might know that it's talking to, it might be able to distinguish that whether it's talking to the verifier or whether it's talking to the extractor. So we need statistical receiver privacy property, which says that an unbounded sender should not be able to distinguish whether the receiver used 0 or 1. And the reason why we need statistical privacy property here is because the prover is going to be unbounded, right? Because we are trying to prove proof of knowledge and not argument of knowledge. So, okay. So how does the extractor proceed? Okay, so I'm going to write from now on. So to describe the extractor, so we're going to define the following terminology. We call a transcript to be good if B prime equals B, and we say a transcript is bad if B prime is not equal to B. So yeah, we say the transcript is good if B prime happen to be the same as B. If it's a bad transcript if B prime is not B. Okay. Okay, so now how does the extractor work? What the extractor is going to do is run the protocol in superposition. Okay, and at the end of the protocol, the final state of the extractor is going to be as follows. It's going to be something like square root P psi good 0. I'm going to explain soon what this means. Square root 1 minus P psi bad 1 decision. Right? Okay, so what does this mean? So psi good is a superposition of all the good transcripts. I mean, this state doesn't just contain the transcript, it also contains the private state of the prover. But yeah, it's private state of the prover and superposition over all the good transcripts. And this is superposition over bad transcripts. Let's just say over. Oh, this is fine actually. Yeah. And this register, what it's supposed to do is you store 0 in that register if B was the same as B prime, or you store 1 if B was not B prime, right? So if the transcript is good, then that means that the extractor's bit B prime is the same as the sender's bit B, right? So you store 0 there. And if it's a bad transcript, B prime is not the same as B, so you store 1 there. Okay.
Sorry, you say we run the protocol in superposition, but if I understood this right, this is just a normal protocol run so far.
Yeah, so
I mean, we just don't measure whether it succeeded. You mean we don't measure anything? That's all you mean, right?
yeah, so you're asking what does this mean? Is that what you're asking?
Well, basically, I have two possible meanings, and you tell me whether one of them is right. So one would just be we just do a normal protocol execution, except we don't ever measure anything, but just put things in auxiliary registers to emulate measuring. And the other protocol in superposition would mean that we actually make a superposition of different protocol runs, for example, with different inputs or something like this.
Oh, no. It's the first one.
Yeah, so it's just making everything unitary as you do also.
Exactly. So,
okay.
So I mean, the way protocol would work is that, you have the prover, verifier, he computes a unitary, and then you do some measurement to send some value to the register, right? Here, don't do anything. Don't do.
Yeah, I get it. I just wasn't clear which possible meaning it.
Okay. Yeah. Okay. And the reason I'm writing the final state to be of this form is so that I can use Watrous rewinding. So just to recall the Watrous rewinding lemma, so suppose, let's say we have a unitary. Suppose we have unitary U defined on, let's say, n plus k qubits, satisfying the following condition. For all psi, which is, let's say H is a Hilbert space, right? For all psi, which is for all n qubit state psi, the following holds. So if you apply unitary U on psi and 0, so in the last k qubits, you just store zeros. You get, I'm going to state the exact version and then talk about the approximate version later. So you get something of the form 1 over square root 2, psi 0, 0 plus square root 1 over 2. Even in the exact version, it need not be half. As long as it's any constant, it's fine. But for now, let's say it's half, exactly half. 1. So then what Water's rewinding guarantees is that there exists another unitary, let's say U prime, such that U prime on psi outputs some state, let's say psi prime, such that psi prime is close to psi 0 in trace distance. I mean, how close, in order to determine how close, you can actually make it arbitrarily close. Yeah. So in the proof of the lemma, you sort of do many rewindings, and if you want the closeness to be some epsilon, then you need to appropriately adjust the number of rewindings in order to get the particular U prime you want. Okay. Okay. So this is what the exact version of Water's rewinding lemma says. But there's also an approximate version, which says that, it need not be exactly half. It can be half plus or minus negligible, right? So even then, you can actually you can come with an unitary U prime, such that U prime on psi gives you psi prime, right? Where psi prime is close to psi 0. Okay. And to see how to apply this lemma in our setting, you should really think of psi 0 as being psi good. Okay. And you should think of psi 1 as being psi bad. Okay. So the goal is to end up with good transcripts, right? Because if you end up with good transcript, if you end up with a state that's just a superposition of good transcripts, then that's the case when B prime is the same as B, which means that the extractor has successfully obtained the first bit of the witness W1, right? So somehow we need to use this lemma to go from this state to just this part, right? Okay, so in order to apply Water's rewinding, we need to argue that the amplitude associated with the good state is going to be something that is negligibly close to a constant, right? So if in Water's rewinding lemma, if this depended on this state, then you cannot apply Water's rewinding lemma. I mean, then all bets are off, right? So to apply this lemma, it has to be the case that the amplitude of the good state has to be negligibly close to the constant. And in some sense, it should be independent of the state you started off with. Okay. Okay, so we need to show that P is negligibly close to half, right? So that's the first goal. P minus half is negligible. And the way we are going to show is using an observation we made earlier. right? So the prover, using the statistical receiver privacy property, we can argue that the probability that B prime is the same as B is negligibly close to half, right? So using this point, what we are now going to do is we are going to run the whole protocol in superposition, right? And so this probability will get converted into amplitude. You will end up with the amplitude of the good to be something like negligibly close to half, and the amplitude of bad to be something negligibly close to half. Let me know if I need to elaborate on this more. Okay.
Sorry, I'm a little confused. I mean, the receiver picks B prime, right?
Yeah.
So can't the receiver, like, why do you need receiver privacy to have?
So you do want to make sure that the amplitude associated with good and bad, the amplitude associated with good should be negligibly close to some constant, right? And if you didn't have statistical receiver privacy property, right? So suppose, let's say the verifier actually gave the bit B prime in the clear, right? So in this case, let's say the prover always sets B equals B prime, right?
Oh, because B isn't released until after B prime. B, you don't like commit to B ahead of time or something.
Yeah, well, it's sort of implicitly committed to, because M0, M1 contains some information about B, right?
Sure, but okay.
Yeah. So you don't want the prover to sort of choose its B based on B prime, right?
Right, I see, okay.
Yeah. So that's why you need the statistical receiver privacy property.
Could you also solve that simply by committing to the bit B? Like a statistically binding commitment? Or would that like mess up other, I guess maybe that would mess up other stuff.
You can, you're saying that, before verifier chooses, just make the prover commit to B. Is that what you're saying?
Yeah. Using a statistically binding commitment.
You can, but in that case, this would follow unconditionally. Yeah.
Right. That's kind of what I was wondering about.
Yeah, you can do that. Yeah. But ultimately, you still need to argue this, whether you argue from a computation assumption or using what you suggested, with that would be unconditional. It doesn't matter. Yeah. Yeah, this follows from statistical receiver privacy property. Okay, so I went over why this is negligibly close to half. I mean, I went over very quickly. So if you want me to elaborate, just let me know. The reason is just that, just run this protocol in superposition. So instead of this, the probability will get converted into amplitude. So, and then you get this, the expression half plus minus negligible, psi good, 0 plus. I mean, whatever necessary to make the sum of squares of these amplitudes to be 1. Okay, so great. So we showed this, which means that we can actually apply Waterous rewinding, right? And get something that is close to psi 0. But psi 0 is going to be close, is nothing but psi good. So we get the following. We get something that is close to final state. and thus you can extract, and Zygote contains W1, right, by the correctness of OT. Right? So we have successfully extracted one bit. Okay. But there is also one more property we want to show, which is that the prover should not be able to figure out whether it is talking to the verifier or the extractor, right? Right. So in order to show this, it boils down to the following property. So when the prover is interacting with the verifier, so the output state of the prover is going to be nothing but, is obtained by tracing out all the registers except its private register, right? Let's say its private register is register X. So you trace out everything except X. In the state, square root P psi good 0 plus square root 1 minus P psi bad 1. And in the case when the extractor is outputting the state, right? The extraction case. So the output state is going to be nothing but trace out everything except the prover's private register in the state psi good. Right. And we want to argue that these two are actually close. Actually, this proof is also necessary in Watrous, and I've not seen this proof written down in Watrous paper and also in subsequent papers. Please correct me if I'm wrong. So this is sort of necessary to argue that the verifier's output state should be computationally indistinguishable in the real and the ideal world.
So you in Watrous paper, it is kind of the conditional state that is indistinguishable, right?
Yeah.
So it would be that if you take the output state up here, measure that it's cat 0, and then renormalize, that would be indistinguishable from the one down there. So this is what Watrous says. And you say that additionally, even if we don't do this conditioning, then the one part of this register is still, you can't tell whether you did this conditioning.
Yes, exactly.
Okay, I see.
Because, yeah, exactly. So the decision register is never made available as part of the final state. Yeah.
Mm-hmm.
And even this proof essentially follows from the statistical receiver property. So I'm going to ask this. So in some sense, we use the statistical receiver privacy property twice. The first time to argue that you can indeed apply Watrous rewinding lemma, and the second time to argue that the output state of the prover is indistinguishable in both the cases. Yeah. Okay. Are there any more questions? Okay. So this was about 1-bit extraction. And here we saw that the extractor can successfully extract with probability maximum close to 1. But unfortunately, the success probability of the verifier is, I mean, the verifier can actually recover the bit with probability negative close to half. So to make sure that the verified success probability is small, what we are going to do is we are going to secret share this bit. this bit W1. Okay. Using I'm being a little imprecise here because the verifier success probability, even after secret sharing, is still going to be half, negatively close to half. But this will make more sense in the when we talk about multiple bits. Yeah. Okay. Okay. So what do we do? So the prover, he has this. He has W1, which is the first bit of the witness. He's going to additively secret share W1 into shares SH1 through SH lambda, where lambda is a security parameter. And then he's going to run the protocol. Which protocol? Well, the protocol, yeah, this protocol, right? So let me call this protocol pi mini. So it's going to run this pi mini protocol, where in the first invocation of the pi mini protocol, the prover inputs SH1. And then it runs pi mini again. In the second invocation, it inputs SH2 and so on. And finally, it inputs SH lambda. Okay. And even here, I'm considering an honest prover. I'm going to assume that he is going to is going to correctly secret share W1 into secret shares SH1 through SH lambda. Okay. And in each of these executions, the honest verifier is going to set the input bit to be 0. Of course, the malicious verifier can do whatever it wants. In the end, we can argue that the probability that from the outputs of the OT, the probability that a malicious verifier receives all the shares of W1 is going to be negligibly small. Okay, this is the intuitive argument. I mean, the intuitive argument follows from the fact that the verifier does not know which of the two positions the prover put the share in. So in each execution, it's going to get the correct share with probability half. And so since there are lambda many executions, the probability that it's going to get correct shares in every execution is going to be negligibly small. Okay. And in terms of extraction, the extractor is going to extract from each of these pi mini protocols to correctly extract the shares SH1 through SH lambda. And then using all these shares, it recovers W1. Okay, so now there are two points we didn't take into consideration. The first point is, what if we want to extract multiple bits and not just one bit? And the second point is, what if the prover was being malicious, right? What if we didn't share his input bit correctly? So we handle both of these points as follows. So the prover, what it's going to do is it receives as input the witness W, which can be broken down into W1 to WL. And then for each of the bits of the witness, it's going to run this whole protocol, right? So let me call this pi. So it's going to run this whole protocol pi for W1, and it's going to run the whole protocol pi for WL. And finally, it proves using QZK protocol, QZK proof of knowledge, not proof of knowledge, sorry, QZK proof system. System that it behaved honestly in all the previous executions. So I already discussed this earlier, so I'm not going to go over in detail. Let me know if you want me to go over this part in detail.
I want just to clarify it for myself. So, because it's, I mean, my intuitive approach would have been to say we have the prover prove in the beginning that there is a witness, and then reveal individual bits, and then we make sure we get them all instead of just part. But here something interesting is happening, because the during the execution, the prover is not. I mean, the prover could still just put in anything, because I mean, while we extract, we don't know that it's the correct witness, because we haven't done this final proof yet. And the curious thing is that if, you can think of this as from all the possible execution traces. So each time we branch into bit 0 or bit 1 given by the by the extractor. So we have this exponential sized tree, and we manage to narrow down to the one point where the extractor has gotten all the witness bits.
Correct.
And then in this point, I mean, at this point, we still don't know whether it's the right bit, but then in this particular point, we run the proof that it's the right witness. And this shows that this particular path had the right, extracted the right witness. Correct. And I find this, I mean, I'm not saying that I see any technical problem, but I find it interesting that, because in a sense, you would intuitively think it's not enough to only have the proof, to only check the proof when in this exponentially rare case that you got everything extracted, but it still works because all the proofs from the other leaves of this infinite tree, they somehow make this particular proof correct. But it's interesting because in the other branches, this proof doesn't really have a meaning, because this proof shows that because there is no such thing as the witness, but instead this proof shows kind of the part of the witness that you have actually extracted is valid.
I see.
In the branches where you haven't extracted successfully, it's not so meaningful. So, I mean, I'm not complaining or something. It's not that I think that something is wrong. I find it actually interesting that you can have this proof in the end and not in the beginning. I
see. So if I understand correctly, what you're saying is the following. So we start with some state, let's say, and this is, I can think of it as two branches. One is a good branch corresponding to W1, and another one is bad branch corresponding to W1, right? And then we have again like good W2, right? Is that what you mean by tree?
Yeah, exactly. And we amplify the one leaf where everything went well.
Right. So you're saying that, yeah, exactly. So we essentially keep going in this direction, ultimately reaching, where we have, I can think of W1, W2, all the, so you are saying that you found it interesting that we have this in the end. Is that what you're suggesting?
Exactly, because I mean, if we would imagine a protocol where we would say, where we would only do the proof, where we would only check the proof if we went along the path where everything went fine, that would obviously not work, because this path actually never happens in real life.
Yeah.
So so we use the fact the proof has to be everywhere in all the paths, but somehow we use it in this unreal path.
Yeah, and I think this is also the same in the leaves in which you actually have the witness is the same leaf in which the verifier is going to also, are the same leaves for which even the verifier is going to accept, right?
I didn't get the sentence, sorry.
Yeah. So my point is that the leaves for which you actually have the witness, right? But we have extracted the witness, are the same leaves for which the verifier is also going to accept this proof.
Yeah.
Well,
the verifier accepts the proof also in leaves where you didn't extract the whole witness. I mean, the verifier gets only half of the witness in typical leaves.
No, that happens with negligible probability is what we show, right? I mean, the verifier cannot accept the proof and the extractor failing. This event happens with negligible probability. Because if you fail in extracting the witness, that only happens when the prover did not use the witness in all these pi protocols.
I was talking about the verifier, not the extractor. So the verifier gets half of the bits.
Oh, the verifier gets half of the bits, correct.
But the extractor with the rewinding gets all the bits.
Right. Oh, okay. I thought you were talking about the extractor.
Yeah. So the verifier checks the proof in the typical leaves. But in the typical leaves, it's not really clear how meaningful, I mean, the intuitive meaning is not clear because the witness is not necessarily well defined.
Mm-hmm.
But anyway, that was just an observation. I'm not sure what I said can be made more formal or something. It's
okay.
Just something I found curious. But I mean, it's a matter of intuition whether one finds it curious or not.
Yeah, I haven't thought about this. I don't know why this is already, it's not a problem. But
Is there any problem if one would make this proof in the beginning? Would the construction work similarly, or is it really important that it's in the end?
Well, if you put it in the beginning, then it is ill-defined, right?
Well, then you would have to commit to the witness and prove that the commitment contains the right witness. So that would be.
No, but then the prover can still cheat and not use the witness bits in the protocols.
Yeah, but then you could in each OT, I mean, you would then need an OT, a committed OT. I mean, one that, I mean, you commit on all the messages in the beginning, and then you make an OT which guarantees that the transmitted bit is one of the commitments. Or you make an OT where you transfer the opening information or something like this.
Sure. You can actually start with a stronger OT protocol that implicitly already has some zero noise protocol, right? Like where the sender is sort of proving that the committed bit is correct. Sure, you can do that.
Yeah. Okay.
Okay. So this is sort of the template for our proof of knowledge system. There are a few things I didn't tell you. The first is, what sort of properties we need from OT. And also how to construct it. The second is proof of the zero knowledge. So Proof of extraction is easy. I mean, you essentially do Water's rewinding for every protocol. So proof of zero knowledge is going to be a little more complicated. You want to argue that we can sort of like put garbage values, and even then the verifier cannot distinguish whether it was actual witness bits or garbage values. And finally, what I described only works in the standalone setting. So third thing is to extending it to bounded concurrent setting. So I can go in any of these three directions depending on what you want. So let me know what do you prefer.
I mean, it seems to me the concurrency is the most difficult. I mean, the first two seem kind of standard. Well, I mean, number two is standard, and number one, I guess you can just use some existing OT protocol.
No, we had to construct the OT protocol.
Oh, really?
Yeah. Yeah. Because
okay, well then,
yeah.
So then either one, I guess. But number two should be standard, right?
So if you start with the OT protocol with simulation security, then it's standard. Then you can sort of extract the bit from the receiver, and based on that, you can either use, right? But if you use indistinguishability security, it's a little more non-trivial.
Oh, I see. Okay.
Yeah.
Well, then either way.
Okay. Any?
But I vote for 3.
You would put 3?
I vote for 3 as well.
Okay. So what about others?
Yeah, I think that's a good idea.
Okay, so let's do 3. So in terms of construction, it's the same construction, except that we're going to use bounded concurrent QZK here. So I spoke about bounded concurrent QZK in one of the previous reading group meetings. So I'm not going to tell how to construct this. So we're going to start with bounded concurrent QZK and see how to get proof of knowledge. Okay, so I must say that this part is a little ugly, so brace yourselves. So the construction is the same. The completeness, the proof of completeness, and also quantum proof of knowledge is also going to be the same, because it doesn't matter whether you're in the bounded concurrent setting or not, right? Since you're only dealing with one prover, so proof of knowledge property holds. So zero knowledge is going to.
So the bounded concurrency property will only apply to the zero knowledge part. So it will not be concurrently extractable.
Yes, yes.
Right?
It will only, yeah, exactly. It will only apply to the ZK part. Yeah. Okay, so right. So, but to prove quantum zero knowledge, we need to sort of redo the proof. Okay, so let's do that. Proof of QZK. So in order to prove that it satisfies quantum zero knowledge, I need to come up with a simulator. So what does the simulator do? Well, let's say it's talking to a malicious verifier, which can initiate Q sessions. So what the simulator does is, for every verifier, whenever it runs the protocol pi, it's going to put some garbage value. So here, the prover was putting the actual witness bits, but here it puts garbage values. And finally, for the bounded concurrent quantum ZK protocol, what it's going to do is it's going to simulate this protocol, right? So it's going to run the simulator for this. Right.
Sorry, I missed something, because the concurrent zero knowledge that you plug in at the end is just going to be secure only against a classical verifier, no?
No, so I'm going to use a bounded concurrent quantum zero knowledge proof system.
But isn't that what you're trying to construct?
I'm going to construct bounded concurrent quantum zero knowledge proof of knowledge. So in order to do that, I'll start with a proof system that satisfies traditional soundness property, and then.
So the BCQK or whatever the acronym is, bounded concurrent zero knowledge already exists.
We construct that in the paper. I mean, I can actually talk about this if you want. The reason I skipped this part is because I spoke about it in one of the earlier reading group meetings.
Oh, I think I missed that talk.
You attended, I think.
Oh, okay.
But it was a long time back, so.
Okay. But then I'm confused what you're showing now. So you already have, if you already have concurrent quantum zero knowledge, then what are you adding here?
Proof of knowledge. So I'm starting with bounded.
Oh, you're showing that it maintains the proof of knowledge property.
No, I'm adding proof of knowledge property. So I'm starting with bounded.
Okay. I see. Okay.
Sorry if this was confusing. So bounded concurrent QZK with traditional soundness. And then I'm going to use OT, meaning these protocols, to construct bounded concurrent quantum zero knowledge with proof of knowledge property, quantum proof of knowledge property. Yeah. Okay. So unfortunately, we make non-black box use of the simulator of bounded concurrent QZK. So maybe let me just quickly go over how this protocol is defined, and then we will see how to use the simulator for this in order to argue QZK for
Can you perhaps explain why this is not trivial? Because right now it looks like, well, replacing the input by garbage, that should be, I mean, you replace the simulator, the original thing by the proof, the proof, or the knot of knowledge, the proof down there, you replace by the simulator. Now it's independent of the witness, and now you replace all your inputs by garbage, which is indistinguishable by the property of the OT. So at the first glance, it would seem that there's no problem. So where is the problem?
Good. So the problem here comes because the prover is simultaneously interacting with multiple verifiers, right? So which means that the OT messages can be interleaved with the zero knowledge messages. Okay. So now let's say you're running the simulator, right? The simulator is going to, simulate the whole protocol, right? So how does it simulate? I mean, it's going to rewind some parts in the protocol. So let's say the OT you want to change, right? There's some OT that you want to switch from using the actual witness to garbage, right? So, but this block, let's say it's going to be rewound, right? So then you don't know how to embed, how to talk to the external challenger, right? How do you non-interactively sort of embed the challenger's messages into the protocol when it is being rewound? Do you see what I'm saying?
So it's about the OTs from other protocol instances that I somehow need to, that will also be rewound, and that, so it's not about the rewinding of the OTs from the current instance.
Yes.
But from the other instances. And
the rewinding is happening because we are using this quantum zero knowledge protocol. So the simulator there is rewinding.
Exactly, but it would then also want to rewind OTs from other protocol instances than the one we actually care about.
Exactly. Yeah.
Okay.
So that's one problem. Another problem is that this is sort of specific to the quantum setting, which is that the simulator runs the whole protocol in superposition, right? And it only measures the decision bit, right, before deciding to rewind. But now the problem is, if you want to reduce to OT, you're talking to an external challenger. So you need to send some message to the external challenger. You don't know which message to send because everything is happening in superposition. Right. So So even that is going to be an issue. Yeah. So these two are the main issues that sort of make the proof complicated. And this was also one of the reasons why I chose. I mean, we talked about indistinguishability security and not simulation security for OT. Because if we started with OT satisfying simulation security, then we would have two simulators simultaneously running, right? Right, each of them trying to rewind a different part in the protocol, which would have made it even more clumsier than what it is. Yeah.
Yeah. Okay. I mean, to see it in detail, I would probably have to try to come up with a proof and fail, but I have a vague idea why it might be not trivial.
Yeah. Yeah. So actually, maybe let me see whether I can give an example.
I mean, I'm happy to take it on trust that naive approaches don't work. I would probably take too much time not to fully.
Okay. So what I can do is the following. So in any case, I have to briefly talk about what this is here in order to show why this satisfies quantum zeroth property. So when I'm discussing this, it will become clear why making this proof work is non-trivial. Okay. So so let me sort of dig deeper into this protocol. This protocol is actually going to be very simple. So we have bounded concurrent QZK with traditional soundness. So this protocol is defined as follows. It takes as input the instance and the witness. The verifier takes as input the instance. And it runs in two stages. Stage one. So in stage one, it executes many slots. So what is a slot? A slot consists of two messages. The prover sends commitment to a bit, and the verifier sends a bit B prime. So this is a slot. And the prover and the verifier run many executions of the slot of a slot. So then the prover is going to convince using a WI that either X is in the language, where L is the language associated with this proof system, or let's say there are L number of executions. Or something like L plus something like polylog L number of slots are such that B equals P prime, right? So the in more than half, something that is significant, some significant fraction more than half. Oh, sorry, it should be L plus L over 2. Something that is slightly more than half. In those many slots, it has to be the case that the verified bit is the same as the bit committed to by the prover. Okay. Okay. So completeness is easy because the prover is going to use actual witness in the WI protocol, and soundness just follows from the fact it just follows from Chernow bound. On average, the malicious prover can only match roughly L over 2 slots, and the probability it can match this is going to be negligibly small, right? Where if L is the security parameter, let's say, or like polynomial in the security parameter, I mean. Okay. So how does the argument for quantum zero knowledge work? So we're going to argue quantum zero knowledge as follows. So the simulator, what it's going to do is it's going to divide the whole protocol into blocks. Okay. Divide all the messages, not just the whole protocol, all the messages exchanged with Q verifiers. So I must say here that L is a function of Q and lambda. Yeah, divide all the message exchanged with the Q verifiers into blocks. And each block has sufficiently large, okay? And in each block, it picks like a verifier, pick a slot uniformly at random, picks, oops, what's going on? Picks a slot uniformly at random. So each block has many messages. It could be WM messages from the first stage and so on. So the simulator is only going to look at the messages where the entire slot is contained inside. Like if one message of the slot is contained in this block and another message in a different block, it's going to completely ignore this message. So the entire slot should be contained in this block. And it looks at all the slots that are there within a block, and it's going to pick one of them uniformly at random. Yeah. And then what it does is it will match this slot uniformly at random. Oh, yeah, sorry, by rewinding. Okay. So, I mean,
match this slot.
Yeah. So by match, I mean that, you know, the verifier's bit is the same as the committed bit. Right.
And then the other slots, it's like not going to rewind them or anything.
Yeah, it will just ignore. Yeah. Right. So the way I have described this, I mean, this is more of like a classical simulator, right? I mean, that's what a classical simulator would do. When it is interacting with like a PPT verifier. But what the quantum simulator is going to do is it's going to essentially run the classical simulator in superposition, right? Just like what was done in Watros. You know, at the end of every block, you store a bit in the decision register that tells you whether the bit was matched, the slot was matched or not, and you measure this bit, and if it was matched, then you move on to the next block, and if it was not matched, then you're going to you're going to rewind using Watros rewinding. And the probability that you match is going to be negligibly close to half. You can sort of, which means that you can apply Watros rewinding. Right? Okay, so is this clear? Oops, I don't know what happened here. Yeah. Oh, I don't know what. Sometimes this happens. Okay. Okay, now let's see. Okay. Yeah, so after matching this is sorry. Yeah, after matching the slot, it moves on to the next block, and so on. Oops, I got another message. Okay. So what we need to argue is that by rewinding, the simulator can match let's say 2 times polylog L number of slots per verifier. Right. So we can argue this if you set the block size to be reasonably large. So you can argue that there are a good number of blocks, such that in each of these blocks you're going to pick this particular verifier's slot with high probability, and so with overwhelming probability for every verifier, the simulator ends up matching 2 polylog L number of slots. And you can also argue that by luck, the simulator can actually match roughly L minus polylog L slots. Or rather, actually, this should be something like 3, I think. Doesn't matter, but 2 number of slots per verifier.
You mean L half?
Oh, yeah, thank you. Right. And when I say by luck, I just mean that, with probability half, the simulator is going to succeed, right? So the expected number of slots it can satisfy is going to be something like L over 2, right? And I mean, well, it's going to be rather L minus 3 polylog L over 2, right? Because 3 polylog L, it has already tried to match. So this is the expected value, and you can argue using Chernoff bound that the probability that you're going to this is the expectation, expected value, and then using Chernoff, you can argue that the probability that you can extract these many slots is overwhelming, right? So now the simulator was able to match these slots by rewinding, and by luck, it was able to match these many number of slots. So if you add both of them, you get L over 2 plus polylog L. Right? Yeah. So so this is very roughly is an argument as to why the simulator succeeds. I see that people are leaving, so let me know what do you want me to do.
Yeah, I think we should probably wrap up in the next sort of 5 minutes.
Okay. Okay. So what should I say here? So we started by talking about how to why is the proof of quantum zero knowledge non-trivial in the proof of knowledge setting. And now that you have sort of seen the simulator, how it works, let me tell you why the proof is going to be non-trivial. So the simulator is it's dividing the protocol into blocks, right? So you have block 1 here. So it runs the whole block in superposition, and then it sort of measures some register here and decides whether to rewind or not, and then it runs the second block and so on. So it could be the case that there are some OT messages here exchanged, right? Let's say this OT1, OT2, OT3. I mean, this could be interleaved with the zero knowledge messages. So now, suppose, let's say you want to argue the security of this OT, right? Some OT execution. How do you argue? So you want to say that, suppose, let's say I switch this, the sender's input value in this OT to be garbage from actual witness. So then the adversary should not be able to distinguish these two cases. If it did, then I can come up with a reduction that breaks OT, right? So how does this reduction work? So this reduction is going to interact, is going to sort of run the verifier, right? And using this verifier, it's going to interact with some external challenger, right, to break OT. So now the problem is, if the OT messages are interleaved with zero knowledge messages, then it does not know when to actually forward these OT messages to the challenger, right? You can say that maybe you can measure some register that tells you whether an OT message was sent or not. But if you measure in the middle of the block, then you can no longer apply Water's rewinding, right? So you have sort of lost some information about the original state, so you can't go back to the original state, right? So, but if you don't sort of rewind and figure out when the OT messages are sent, then how do you interact with the external challenger? Right. So this makes arguing, invoking OT security in the proof non-trivial. If Dominique is there, does this answer your question? It's probably not there. Oh, is there?
Dominic, I think you're muted.
No, I'm muted. So I would have to think longer about this. So I can't really, but I don't have any questions right now.
Okay. Okay. So yeah, I couldn't do the proof, but this hopefully gives some intuition of the challenges involved in proving the security here. Yeah. Are there any other questions?
Okay, seems not. So thanks, Prabhanjan. Let me just stop the recording.